Lots of stuff happening because it's the end of the semester. You've just submitted a homework assignment. You've got another one due on Thursday. So that's kind of bad, having 2 homework assignments due in the same week. It's the last week. But I thought I'd balance things out by making the lab that we're doing today the sort of more of a demonstration than a lab. It'll have some calculations associated with it. But if you set it up on a spreadsheet, you could do those calculations in like 11, maybe 12 minutes. Or if you did it by hand, we're talking 25 minutes. So let's go from the top. Today, during lab, you have to submit your Water Gems 2 report. And again, I'm going easy on you there because it's, remember, not just a report, it's screenshots and some short answers. So I hope that you enjoyed using Water Gems. I'll see Group A at 2 o'clock and Group B at 3. What we're going to do in lab is work with the pipe rack again, this time using the pressure meter to characterize the drop that is experienced for some of the local losses, sometimes called minor losses. Remember I told you how minor losses is a derogatory term for local losses. So we're going to characterize some of those local losses using the pipe rack today. And remember, I said that there's going to be some N2 students around. We were originally told that there would be 160-something of them, but I just got an email a few minutes ago saying that only 70 showed up to the morning portion. So it'll probably dwindle even further by the afternoon. There may be a handful of students like hovering over you, watching you quantify the flow rate during your lab today. So you can do the experiment, and it'll probably take you half an hour to collect the data, and you could use that second half hour to do the calculations and give it to me today. But I'll give you any time between now and the end of the semester. You can give it to me on the day of the final if you want to give me, if you really like dragging things out and procrastination is your game, bring it to the final. And that'll be like your badge of honor that you're a procrastinator, is handing in lab 13 before you take the test. All right? So that's the labs. Homework 7B will be due on Thursday. It's relatively straightforward, just going along with grade lines, which we'll tackle today during the lecture. I've got a handout at the end of your lecture notes that you'll get some practice drawing grade lines. Now the final exam is probably on your minds. We've got about 9 days, and less than 9 days, before you take the final exam. You can prepare an equation sheet, 1 page, front side only, so write small. And it's going to be a comprehensive exam, but there's added emphasis on the material since the last midterm. So what material am I talking about? Chapter 7 and Chapter 8 will only have 1 day covering Chapter 8. That'll be Thursday's class. There will be the depth of the questions, like the technical complexity of Chapter 7 and Chapter 8 questions will be higher than those from other chapters. The questions that you'll get from Chapter 2 will be relatively basic and straightforward. I'm not going to expect you to have the same exact recall now that you did when you were taking the exam for Chapter 2 and 3. So, comprehensive exam, it would be impossible to write an exam that was not comprehensive. So that's the way it's going to be. Any questions about these announcements, what's happening today, what's happening this week? We'll have some time to talk a little bit more about the final exam on Thursday. Also on Thursday, we'll have some time set aside for you to complete the course evaluations if you haven't already done that. It looks like I get an email every day telling me how many students have finished the evaluation. It doesn't say who said what, obviously, but it's just they send out reminders to the professors to keep telling you guys to do the evaluation. So if you haven't done it by Thursday, we'll have a little bit of time that you can use the tablets or your own computer to finish those. All right. So no questions. We're going to get right into talking about grade lines. In lab today, we are going to be observing local losses, and here's just an example of one kind of local loss and what causes a pressure drop when there is some sort of a transition. A transition may be that the flow direction is changing. A transition can be that the speed of the flow is changing. And so when the pipe diameter increases like that, the velocity goes down. Now there's actually two things simultaneously happening in an expansion, and that makes it a little bit confusing. So let's talk about the expansion before we get into hydraulic grade lines. What does Bernoulli's equation say will happen at an expansion? When you have velocity is big at 1 because it's a small diameter, and velocity is small at 2, what does Bernoulli's predict would happen in a transition like this? The pressure is going to change. So is the pressure going to go up from 1 to 2, or is the pressure going to go down? The pressure is going to go up, right. And let's remind ourselves why. Bernoulli's equation says P1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G. So since they're on the same horizontal datum, Z1 and Z2 are equal, so I cancel those out. So what we're saying is that the velocity was big and now is small. So all of that energy that was tied up as velocity is going to go into added pressure at 2. And so Bernoulli says that P2 is going to be bigger than P1. So in other words, pressure goes up. And we could calculate how much the pressure goes up by comparing the velocities. Like the pressure increase, we could calculate delta P just by knowing V1 versus V2. And in fact, we've done that in an example. We looked at how a pressure change was a function of a change in velocity. Okay, so Bernoulli says the pressure is going to go up. What do we know about local losses? What do they do to pressure? They're not called losses for nothing. It decreases energy. It decreases pressure, right. So you'll notice that there's a zone of separation that's indicated here. They're like a swirling vortex. This swirling vortex is not so great for conserving energy. There's a loss of energy here because of the turbulence. And so pressure is going up because of the increase in diameter. But at the same time, you're losing some pressure because of the local loss. And so, like, how would you interpret this in the lab? What you'd do is you'd measure the velocity at 1 and the velocity at 2, and you'd do your hypothetical calculations according to Bernoulli's, and maybe it would say that the pressure is going to go up by 10 kPa. And so you're expecting, when you plug it in, it's going to say the pressure difference is 10 kPa in the little handheld meter. But because of the energy losses, you'd plug it in and it would maybe say that the pressure increased only by 8 kPa. And so the difference between what you expected, that 10 kPa predicted by Bernoulli's, and the 8 kPa that you're measuring by the gauge, that's how much energy was lost due to the fitting itself. Most of the fittings aren't as confusing as this because the velocity in and the velocity out are the same. So take, for example, a 90-degree bend. When we're in the lab today and we are plugging in the gauge here and plugging in the gauge there, and it's going to our little meter, it's going to tell us maybe 8 kPa. And all of that change will be because of the bend. When the water is going around that bend, it's swirling around and there's a vortex and turbulence, and so energy is lost at the transition. And so it's only going to be in a handful of fittings where there's either a pipe contraction or a pipe expansion where we have to think a bit deeper, where the pressure change isn't only because of the loss, where there's simultaneously like a Bernoulli effect happening and a loss at the same time. That usually won't be the case. So as the equation says there on the screen, the head loss can be calculated as a function of the difference in the velocities. And in the handout I've given you today, turn to the second page of the handout where there's K values, typical K values. What you'll be doing to find out the head loss is you'll be multiplying this K value that's listed by the velocity head term, by v squared divided by 2g. And so for the 90-degree T, for example, that's whatever the velocity is through the pipe, square that, divided by 2g. So you get the velocity head, and you multiply it by the K value of 1.8, and that tells you how much energy loss you should expect through that fitting. So, you know, the predicted energy loss, if you have some K value for a 90-degree bend of 1.8, then the head loss would be 1.8 times v squared divided by 2g. And then you know the relationship between head loss and the pressure change is that head loss is delta P divided by gamma. So in the lab today, you know, we're always doing comparisons, right? What's the predicted value versus the measured value? Well, I've got a table of typical K values, and I want you to calculate the actual K value that you observe in the lab under the experimental conditions today. So most of these are going to be pretty simple, but you'll notice the last two for sudden contraction and sudden enlargement. I mentioned that it should be for the contraction, the K value is in reference to the outgoing velocity head because there's two different velocities. So in this particular pipe rack, they have referenced the K value by the outgoing velocity head for the contraction and the incoming velocity head for the enlargement. One other thing I want to mention about the lab before I move on is that there is 3 different routes through the pipe rack for today's experiment. You're only going to have to quantify the flow rate 3 times, which is nice because if you look at how many fittings there are, you'd think, oh no, I'm going to have to quantify the flow rate 1, 2, 3, 4, 5, 6, 7, and so on and so on. But you don't. You're going to have to plug in the gauge to a certain number of, you know, for each of these fittings you're going to have to plug in the gauge, but you're not actually going to be changing the flow rate at all. You can get multiple measurements without changing anything about the flow rate. So on the data table, you'll notice that you're only going to do the standard flow rate measurement thing where you're dropping the ball into the plug and using the stopwatch. You only do that 3 times today. That'll speed things up considerably. All right, so that's all I wanted to say about local losses today, unless there's any questions about that. Grade lines is a way of visualizing energy in the system. It's a way of like sketching how much pressure is there at a certain point. Grade lines are actually, it's not just an educational thing. Grade lines are used in plans of water treatment plants and wastewater treatment plants so that the designers can make sure that pumps are used in as few places as possible, because you can really spend a lot of money on electricity when you're treating water if you're not careful. You know, the best water treatment plant is one that's getting its water from the mountains and is able to configure where each of the chambers are in the treatment plant so that everything flows by gravity. And there are a handful of treatment plants that succeed in that, where they really don't have electricity, maybe for, you know, metering out the chlorine into the chlorine contact chamber, but all of the major steps in the treatment chain are done by gravity flow. And the way that they're able to accomplish that is by, in the design drawings of here's the pipe and here's where the valve is going, they have a sketch right on top of that drawing that's showing what is the energy grade line and the hydraulic grade line. So as you'll notice from the image on screen, EGL, that stands for energy grade line. HGL, that stands for hydraulic grade line. And the energy grade line is always above or on top of the hydraulic grade line. Hydraulic grade line is never the one that's on top. And the reason for that is, here's the definition of the two. The energy grade line is all three terms of the energy equation. Energy grade line, EGL, is P divided by gamma plus Z plus V squared divided by 2G. So at any point in the system, you can find out how much energy is there by adding up the sum of those three terms. And so the energy grade line is just connect the dots of where is the energy at every point in the system and draw a line that describes how much energy is at each of the locations. By contrast, the HGL, hydraulic grade line, is only the pressure head and the elevation head. It does not include the velocity head. So hydraulic grade line you can think of as like potential energy. An energy grade line is potential energy and kinetic energy, because it's the velocity head that's the kinetic term in energy. There's so much happening in this image. We're going to look at it for a little while. Water is flowing in this image from a tank through a pipe, and then it's discharging as a jet into the open atmosphere. Okay? So starting at the beginning, the energy grade line and the hydraulic grade line are at the surface of the water tank, and both of them are in the same place. And so let's look at these formulas and try and figure out why is it that the energy grade line and hydraulic grade line are at the water surface. All right? Both of these measure energy. And so how much energy is there in the system right here where my finger is, in the middle of the tank? How much energy is there right there? Okay, well, in the tank the water's not moving unless we're really close to the pipe. You know, the water's sort of getting sucked into the pipe over here. But let's assume that here there's literally no movement in the water in the center of the pipe. Okay, so relative to this datum, we're measuring elevation according to, you know, this is 0 elevation. Where is the energy right here where I'm pointing? There's a little bit of Z because I'm above the datum. Where else is there energy? Not V, so that narrows it down. There's pressure, right. So how much pressure is there? How much pressure is there in the middle of the tank? What is it dependent on? Yeah, the height of the water above it. So we can always calculate P is delta H times gamma. Okay, so it doesn't matter where I am in the tank, but the amount of energy is the same. You know, what if I go to almost to the top of the tank? You know, when I'm really close to the top, there's not much pressure there, right? So why is it that there's the same amount of energy at the top of the tank as there is at the bottom? There's a lot of Z, but less pressure. And as we move up and down through the tank, there's the same amount of energy. It doesn't matter where we are in the tank. And so that's why the energy grade line and the hydraulic grade line are flat here, and they're on top of each other. Is because, you know, HGL equals EGL if there's no Z, which is the case here. And we've got that exchange and balance of potential energy going between the pressure and the Z. All right, so let's get closer to this entrance. We know that the water is sort of accelerating. It's going from 0 velocity and it's accelerating to have some positive velocity towards the right. What's that called when water is accelerating with respect to position? Convective acceleration, right. So that's non-uniform flow when the velocity is changing with respect to position. Okay, so here we have some convective acceleration, and what you'll notice is that the EGL and the HGL are beginning to diverge. You know, they draw it as a straight line just for simplicity. Probably not a straight line because, you know, this is like a curved surface. If we really wanted to be super accurate about, you know, what's the velocity at each of these points, we could try and describe this, but they're a certain distance apart. You know, once we go through this transition where they were on top of each other and now they're apart, how far apart is the EGL and the HGL? Oh, it depends on the velocity head term. So this term that I've just circled here, it's the velocity head term. And you'll notice on the drawing right here, they're saying how far apart those two lines are. It's far apart by v squared divided by 2g. And these two lines are parallel. The EGL and the HGL are parallel because the velocity isn't changing anywhere. Why do you suppose there's a downward slope on the EGL line? What does it represent when the line is going down? You're losing energy, right. And so the steeper the line, the steeper that downward slope, that means you're losing energy at a faster rate. If we had an inviscid fluid, what would the EGL and the HGL look like? My gesture might have given it away. It would be horizontal, right. Why would the EGL and the HGL be horizontal if it was an inviscid fluid? You're right, because the inviscid fluid is the one that is so inviscous, has no viscosity, so it isn't affected by the roughness of the pipe. It can just slip right over the surface of the pipe with no losses whatsoever. Of course, that's not real, but it brings up an interesting point, is that a different kind of fluid is going to have a different slope as well. Like, what if we have a fluid with very low viscosity, like if we have isopropyl alcohol going through there? Well, that slope wouldn't be very steep because isopropyl alcohol has a low viscosity compared to SAE 30 weight oil. That would have a very steep slope because the oil has a higher viscosity. It's going to be more directly affected by energy loss. So what you should write in the margin is that the slope of the line is a reflection of energy losses. And the rate of energy loss is the slope of the line. So what is the slope of the line? It is delta H divided by L, whatever the length of the pipe is. And the delta H that we're talking about, those are head losses. So I shouldn't just say delta H. Maybe I should say H sub L. And those H sub L, that includes the friction loss H sub F, which we talked about previously, and we're going to talk about a lot next semester. And then the local losses, H naught, which we'll delve into a little bit during the lab today. Okay, so let's take a pause for a minute. Any questions so far on this drawing or the concepts that go into it? Why does the energy grade line, like if you had a conceptual question, if at some point in the next 0 to 10 days you have an opportunity to answer conceptual questions related to fluid mechanics, what if the question was, why must the EGL and the HGL come apart? They were on top of each other. As water flows through the pipe, how come they have to come apart? Yeah, because there's velocity in the pipe. And so the distance apart they are, it's necessary because there is velocity in the pipe. Okay. Anybody remember what this kind of a tube is called? When you puncture a pipe and you put a little tube that goes upward vertically, and you got to make sure the tube is tall enough to contain all of the water that will fill it. It's a piezometer, right? And so a piezometer measures only the potential energy in the system. It doesn't measure the kinetic energy that's in the liquid. So this piezometer that's here, you could label that on your drawing. You'll notice that the water level rises in the piezometer to the HGL. That's super convenient. What a coincidence that it rose right to where the HGL is. Actually, that's how you draw the HGL. You know, if you were doing an experiment on a physical system and you wanted to sketch the HGL, like on the chalk on the wall, like trace it, you'd drill holes into the pipe and see how high the water level rise. And that's what happens with the HGL and the piezometer. What about this other tube? How come the water is rising even higher? Look, it's not super noticeable, but the water level's higher over here than it is there, and they're drawing the EGL through this line. Who can explain that? Okay, why? You're right. Why is the velocity affecting that? You got that 90-degree bend that's sort of like looking, it's blasting, the water's blasting it right into the opening. And what do we call it when a streamline is moving along and then all of a sudden stops? Stagnation point. And so the added increase in elevation because of that 90-degree bend and the blast of water, that stagnation point, well, it just so happens that the added energy boost it gets above, if this bend wasn't there, it would just be an ordinary piezometer. And so the water level would have been down here. But because of that bend, it's rising up an elevation equal to the velocity head. And so in other words, the stagnation tube is saying, I'm going to take that energy that's associated with the velocity head, and the water level is going to rise a little bit higher because of that. All right, so the water is sloping downward. You'll notice that they're saying here, at any point, you can know what the head losses are. Now this HL, that's not the head loss for the whole system. That's just the head loss at what they're calling location 2, right here. You know, if we go over a little, the head loss is going to be more. You know, if we're saying, now I'm interested in this point, well, the head loss is from the energy grade line all the way up to the horizontal surface that's described by the water surface. Okay. All right. Now they've been a little bit sloppy in my opinion. I think they should have kept the HGL. I think it should have intercepted right here, but I mean they can make an argument that, you know, they've got it so that the HGL stops at the center of the opening. It's a minor point, but the major point I wanted to tell you about is why is it that the EGL isn't touching the water surface here while over there it was touching the water surface? Why is the EGL above the water surface here and over there it was touching the water surface? There's still energy, right. So the water's moving, it has velocity, and so the distance between the water surface and that EGL, you have to put it above there to acknowledge the fact that that water still has kinetic energy. So there's still a velocity head associated with it. All right, that's a lot of thing to put in your drawing. And when I include an EGL, HGL problem on the final exam, what I'll usually do is there will be maybe 10 things that you can, 10 characteristics you can represent in the drawing, and if you've got 6 of the 10 at least, then I give you full credit, and if you miss, you know, if you only have 5, then I take off 1 point. I just, you know, I've developed these questions where I'm looking for you to take into consideration certain things in the sketch. So let's get some practice with these sketches and different types of hydraulic features and what they do. We've talked about how a pump adds energy, and the common misconception is that the pump speeds up the water. You know, that the way that the pump directly adds energy is by speeding up the flow. And as I've mentioned before, and it bears repeating because it's a little counterintuitive, if you've got 2 reservoirs connected by a pipe and you've got a pump in there, the way the pump works is not by speeding up the velocity, because the velocity in and the velocity out is the same. What the pump does is it adds pressure to the system. And that's what's being expressed here in this drawing on the screen, is that you'll notice that there's an abrupt rise in both the EGL and the HGL, but the distance between the two is the same. You know, how far apart they are is an indication of the velocity head. And so if the velocity out was bigger than the velocity in, then those two lines should have a different distance apart, and they don't. You'll also notice that they have the same slope, which means the energy is being lost at the same rate. And fast-moving water loses energy at a higher rate. And so another, like, some of the clues that you can get from an EGL drawing is if you've got a really steep slope, and that can either mean maybe that the pipe's too small, or that the velocity's too fast, or the pipe's too rough. You know, whatever the case it may be, energy is being lost quickly. But here, the slope of the lines coming in and out of the pump are the same. So those are some visual clues that the velocities haven't changed because of the pump, in versus out. I mean, of course the velocity is different than if the pump wasn't there at all. You know, in this drawing, if the pump wasn't there, or if the pump was switched off, it's just going to be a trickle. It's going to be going from tank to tank very slowly. But as soon as we kick that pump on, and the pump adds a lot more energy in the form of pressure, then the water is going to be moving faster. Because if the pump is adding, let's say that this elevation is 10 meters, and this elevation is 3 meters. So right now there's a 7-meter energy differential that's driving the flow. Well, if we kick on the pump and the pump is adding 10 meters of head, that's exactly as though we had raised this by an additional 10 meters. And so it's sort of like, you know, increasing the driving force, and so the velocity through the pipe will be faster. But it's important to distinguish cause and effect. The effect is the faster velocity, but the cause is that the pump is adding pressure. So that's another great conceptual question for exams, is explain how pumps add energy to a system. And you'd say, well, the rotating impeller in the pump accelerates the flow and adds pressure to the system. Because you read the book and you know that's what it said in the book. Right. Any questions about pumps?
I'm just a little confused why, like, when water's flowing through a pipe,
Yeah.
and it changes diameter, we have the velocity and the pressure are changing in opposite directions.
Yeah.
But here we're increasing pressure and increasing velocity.
We're not increasing velocity in steady state. You know, there's two things to keep track of. There's upstream versus downstream. And that's completely separate from before versus after. Okay, so let's consider the upstream versus the downstream. So the pump is on. Upstream versus downstream with the pump on. So when the pump is on, upstream has low pressure, downstream has high pressure. Because that's how the pump works. The pump just increases the pressure on the downstream end. Now, before versus after. Before is pump off, and after is pump on. So when the pump off, the velocity is slow, and when the pump is on, the velocity is fast. But the velocity is fast because pressure was added. So that's what I mean by it's important to keep the cause and effect separate, is that the fast velocity is the effect of the increased pressure. So it is confusing because, you know, Bernoulli's equation says that if the pipe diameter is the same, the velocities will be the same and the pressures will be the same. So the short answer is that this is not a Bernoulli's. Bernoulli's doesn't describe what's happening here. The energy equation does. I'm glad you asked that. Patrick.
Since the velocity is increasing as well, or does that mean that the pipe diameter?
No. The velocity is increasing compared to when the pump was off. But the velocity is the same. So if we're just looking at upstream versus downstream with the pump on, low pressure, high pressure, velocity, same. you know, like both of the velocities are the same. The velocity in and the velocity out are the same, but the pressure is different because what's between the upstream and the downstream location is the pump. So the diameters can be the same. Yeah. Okay. How does a turbine work? Well, it works in the opposite way from a pump. Remember, a pump immediately boosts both the EGL and the HGL, and because a pump adds pressure, a turbine takes pressure out of the system. All of the water pressure of this elevated reservoir, that pressure is sort of pushing the blades in the impeller. That's why the impeller turns, is because on the upstream face of the impeller is this really high pressure of, you know, a certain height of water. You've got all the pressure in this pipe because this tank is elevated. You know, you lost a little bit of energy due to frictional losses through the pipe between the reservoir and the upstream face of the turbine. You know, you lost a little bit of energy due to friction losses, but still there's a lot of pressure in there before the turbine. But then suddenly that turbine extracts the pressure because it's spinning around and the downstream face of the turbine has a lower pressure, and so suddenly the water that comes out of the turbine has a much lower velocity, a much lower energy grade line and hydraulic grade line. So that's why there's that vertical drop-off there, is because turbines extract pressure from the system. The other thing that's a little bit kooky about this drawing is look how the diameter, it's sort of like gradually increasing. And so they've tried to capture that here. They've shown that the HGL is getting closer to the EGL. And so when the two lines aren't parallel, that tells you that the velocity is changing. And so as the diameter gets bigger, the velocity is slowing down, and the two lines are getting closer together. Why is the EGL and the HGL on the surface of that reservoir? No velocity. That's right, because as whatever energy there was, you know, like whatever velocity head there is before the pipe goes into the tank is lost as soon as the discharge goes into the tank. And this drawing doesn't show that very well, but I think I have another drawing that shows it better. Do I? Yes, here. Okay. Before we get to that one, let's just look at a nozzle. This nozzle shows the diverging EGL and HGL pretty nicely. And does it make sense that the EGL and the HGL have to get further apart? So what we know from continuity equation, chapter 5, tells us that big diameter means big cross-sectional area, so the velocity is slow. But as the nozzle contracts, the velocity increases. So now we've got a big velocity. So how does that affect both the pressure and the energy term? Okay. Well, let's look at the EGL first of all. It's not horizontal, which means energy is being lost. But what do you notice? It's not super obvious here. It's kind of subtle. But what happens to the slope of the EGL once the nozzle has contracted? What did you say? It starts decreasing more. Yeah, you can see that this line is a bit steeper than it was here. And so that's a reflection of when the velocity is higher, you lose energy at a faster rate, because head loss due to pipe friction is a function of FLV squared divided by D2G. This is Darcy-Weisbach equation. You don't need to remember it specifically in this course. You will next semester. But generally, the concept that you should be acquainted with and comfortable with is that energy loss is a function of velocity squared. And so if velocity increases just a little bit, that can have a huge impact on the rate of energy loss due to pipe friction. And that's what you're seeing here. in my opinion, they haven't. They should have made that even steeper. They should have made it more obvious, because your velocity is going up a lot when the diameter contracts so extremely as it has here. The velocity is going to really go up, and so they should express that your frictional losses will be going up a lot too. But they've just sort of gotten at it a little. Why is the HGL getting so much further away from the EGL? Well, the hint there is that the difference between them is the velocity head, and of course as the velocity goes up, then so does the magnitude of the velocity head, so the EGL and the HGL have to get further away. And then the last characteristic to note, we've seen it before, is that a water jet continues to have energy after it exits the conduit, and so the EGL remains above the jet even after the water comes out of the nozzle. All right, here's the one that I think tells us some more interesting things about the rate of energy losses. Okay, so there's the before the transition and after the transition. Okay, so starting at the very far left, the water comes into the pipe, and then that's the cause of the divergence between the EGL and the HGL. They used to be coincident with each other. They used to be right on top at this tank, and then they came apart because of the transition. This is relatively shallow slope, and this is a very steep slope. Why? Yeah. So here you've got a small diameter, which means the velocity is big, and big velocity means a faster rate of energy loss. And so that's why this line is so steep. And that difference in velocity is also the explanation for why the EGL and the HGL are so much further apart in that second pipe segment. So the other thing that you would definitely need to capture is that show the velocity head is bigger in this second line segment. All right, what do you think these little blue lines here mean? What is that meant to represent? It's sort of like turbulence. There's this jet of water, and it has, moving water has kinetic energy. But as soon as that moving water discharges into a tank, all of its kinetic energy, it's just lost. Poof, it's gone. Maybe it heats up the water a little bit, not much. You probably couldn't even measure it. But look at this sudden drop. The EGL, right on the left side, inside that pipe, it still has kinetic energy. This much kinetic energy, a fair amount. But then as soon as the water gets into the tank, poof, all of that EGL is gone. The EGL and the HGL are right on top of each other again in a open to the atmosphere tank where there's zero velocity. And so there's an outlet head loss. And we'll do this a lot in hydraulic engineering when we're being really meticulous to identify all of the losses in a system. We will account for what's called an exit loss. When a pipe connects to a reservoir or a tank, all of the kinetic energy that it had in the form of velocity head is lost when the pipe discharges into the tank or reservoir. All right, here's kind of a funny one, because the pipe is going up and then the pipe goes down again. And you wouldn't expect it, but the elevation of the pipe actually has no impact on the EGL or the HGL. You'd think maybe that the EGL and the HGL would have to be affected because, these were horizontal pipes, so we're thinking, oh, maybe the EGL and the HGL were these neat lines only because of a horizontal pipe. But this actually lets you know that the physical location of the pipe doesn't matter. And let's try and tackle why that is. As the pipe gains elevation, it's getting more Z. And so it seems like the HGL should be getting bigger, right? As the water goes up, it's getting more Z. So why isn't the HGL getting bigger? Here's the HGL. It's a graph of Z and the pressure head. So you'll notice, though, that as we go uphill, the HGL isn't getting any larger. Why is it? Yeah. So as you go uphill, you may be gaining Z, but you're not like inventing energy. You're gaining that Z at the expense of a loss in pressure. And so as the water flows through this conduit upwards, the pressure is decreasing, actually for two reasons. For one, you've got the energy losses. And, you know, the energy losses is why there's a downhill slope on both of these lines. But then that issue aside, the other thing is that you're losing energy just because of the hydrostatic equation. You know, this really is the hydrostatic equation, that the balance between elevation and pressure. And so pressure is getting lower and lower. And actually, if the physical surface of, if the physical location of the pipe goes above the HGL, then that means we're in a negative pressure zone. So remember piezometers? We talked about them earlier today, where a piezometer is just, you know, water's flowing through a pipe and water has pressure, and if you puncture a hole, then the piezometer, if you attach a tube to that, the water level will rise, and that tells you how much pressure is there. What do you think would happen if we punctured the pipe here? Yeah, but why? Before it quit flowing, like it would suck air in there. Right, yeah. It would have suction instead of pressure. So you connect a piezometer, instead of water rising to a certain elevation, it would actually start sucking air into that location where you puncture the pipe. And so you'll notice that there's a negative pressure head. So if you connected a differential pressure gauge, then rather than rising to a certain elevation, the water would be going down to the hydraulic grade line. Everything's cool as long as the exit of the pipe is below the hydraulic grade line. It's funny you'd mention that, because there's a device called an inverted siphon. Like if you had, and I've seen an inverted siphon before. When I was visiting Utah, there's these mountains, and you know, there's a river coming out of the mountains, and they wanted to get water over here to like a plain, but there's this valley underneath. And so what they did was they put in a pipe, and it goes all the way over here, and then it comes out. And so they're capturing the water going under the valley, and as long as, let me draw that a little bit differently, as long as the inlet of the pipe, here's the water coming out, so the water goes in, as long as the in is higher than the out, it's okay to have the water go down and then up again. It's called an inverted siphon, and it's an amazing thing to be standing on the edge of essentially a cliff and looking down, and then all of a sudden like a canal starts, and you're thinking, well, where does the water come from? But it's coming from that mountain a couple of miles the other direction. So here it's the same situation, where as long as the outlet of the pipe is below the inlet, the water will continue to flow. And you can think of it like when you're filling a swimming pool. If you want to drain a swimming pool, you put the hose in the swimming pool, you kink one end of it, and then you take that end as low as you can and open it, and then it'll start to flow.
I was just going to say, that's kind of like, I think that fish tank, you drain your fish tank, you just suck it, and
Right, yeah. And the interesting thing is that, you know, as long as the outlet of the fish tank is in the tub and the inlet is in the fish tank, you can move the rest of the tubing around and it doesn't change the flow rate. You can have the middle part of the tubing, you can take it high, you can take it low, and it affects the pressure inside the tubing, but it doesn't affect the flow rate through the pipe. And so this brings up an interesting point, is that Remember, what happens when pressure gets really, really low? Cavitation, right. You can make water boil or go from a liquid to a vapor by having really low pressure. So that is the one thing that you kind of got to be keeping tabs on, is you want to know what's the vapor pressure of the liquid. And you know, maybe that tube, if you took the tube too high, the little plastic tubing could collapse on itself. You know, it may not have the structural integrity to handle a negative pressure. It might just, you know, like collapse and the flow would stop because that suction sort of brings the tubing together. If it was a metal pipe, it probably wouldn't, but you could have cavitation inside the pipe, and then that could erode the material over time. So it's an interesting case. Other questions or comments related to this? All right, so turn to the second to last page in your notes for today's class. And, oh wait, no. What are we doing here? Oh, last slide, all right. I got ahead of myself. I guess what I did is I put in arrows to indicate, just reviewing, there's the divergence of the EGL and the HGL when it goes from zero velocity to a positive velocity. Another characteristic you always have to integrate into your drawing is the slope is indicating a friction loss, and you know, how steep should you make it? Well, you have to know that your EGL, when you're drawing this line, you want to have your EGL start at the water surface and end a little bit above the water surface here. So drawing these is sometimes like an iterative thing. You definitely should draw them in pencil, not in pen, until you've got some practice, because you'll make something a slope too steep and then you'll realize it's below the outlet tank, and that's a mistake. So all right, let's do that handout. I'd like you to get with a partner and try to draw the EGL and the HGL for this first one where you're connected by two tanks. And then I'll give you 5 or 6 minutes to do that, and I'll show you on screen what my drawing looked like. All right, forgot. I won't start from the beginning. So they're supposed to be parallel to each other because the rate of energy loss is the same. And then there's a sudden expansion, and you lose some energy because of that sudden expansion. Now, as I've drawn it here, I'm assuming that you are losing more energy from the expansion, more pressure from the expansion than you're gaining due to the Bernoulli effect. But you didn't have to necessarily assume the same thing. You could have put together a drawing whereby the HGL actually is higher coming out of this transition, because we know from the Bernoulli effect that when the velocity is low, that the pressure increases. And so, you know, depending on how big the pressure increase is compared to how much energy is lost, you could have the HGL above, the outgoing HGL above the incoming HGL, but what you have to have is there's some kind of loss there. And so that loss is like a sudden vertical drop. The EGL can't. The HGL, you could have said that the increase in pressure due to the Bernoulli effect is exactly equal to the decrease in pressure due to the energy loss. So the HGL could intersect each other, but the EGL has to be below. And so I'm going to put in here as a required characteristic a local loss means a vertical drop in EGL. So what we got so far is the EGL is labeled and above the HGL. The EGL and the HGL diverge at the tank. Because it's a smaller pipe upstream, that means you're having a bigger velocity, so that's why the slope is steeper. That's why you've got a bigger velocity head between the two. And then at that larger pipe, so I'm going to put here large pipe means low velocity. And since it's got low velocity, that's why the slope of the line isn't as intense. You know, you're losing energy at less of a rate. So slope is shallow, not sallow, shallow. And the velocity head is small. And velocity head small means that the EGL and the HGL are closer together. All right, and then the one last characteristic that's required is that the EGL immediately drops at the discharge into the tank. And that's where all of the remaining energy is lost as the water flowing through the conduit discharges into the tank. So all of that velocity head just goes away. And that's why this line is above, but the HGL ends at the water surface. The EGL ends somewhat above it. So it's hard, you know, if you were to draw this too steep, then you end up below it, and you don't want to be there. And you know, I drew this pipe going down and then up again just to illustrate that same point that was made in the previous slide, in this slide, that the location of the pipe doesn't affect the EGL or the HGL. That's why I had that dip down like that. Any comments or questions? Okay, take a crack at the last one. We've got about 5 minutes, and then I'll show you what my solution looked like for that one. This one has a pump in play, so we'll see what effect the pump had. Here's what easy does it. Here's what I had. So it's labeled. The EGL is above the HGL. Again, it seems like I can't draw a parallel line to save my life. Those are supposed to be parallel. Let's assume that they are.
Are they supposed to be at the pump when it comes down?
It doesn't have to touch the pump. No, it could have been, I could have made it up here. It could even be below the pump. It's just, I'm glad you asked that. It's just coincidental that it's bumping into the pump itself. Yeah, good question. Yeah. Yeah, it goes from, let's assume it's all the way full to the surface, and so that's why it's up here to the edge. We have the induction period where they're diverging. Velocity head is big because this is a small pipe, whereas this thick pipe, you'll notice that the lines are closer together, and also the slope of the line isn't as steep for the same reason, because the velocity is lower. The EGL is a little bit above that discharge tank. This one's complicated because, you know, those tanks are shown in isometric view, but the main thing here is that, you know, the water can't flow uphill. Like the most common mistake I see on the exam when we have this is like people saying, well, there's a pump here, so the water's going up, and then it's going up even more. There's always going to be energy losses. It's still going to be down and then a sudden boost and then down again. That's how it works. That's why it's drawn that way. So there you have it, EGL, HGL, the end of Chapter 7. You got your assignment to submit on Thursday, and then on Thursday in class, we'll jump into Chapter 8. See you at lab.